In some previous videos, we've looked at how to actually use the durable functions, how to implement them. This video, however, we're going to look a little bit deeper and figure out how this magic of these stateful functions actually work. Let's check it out. Azure functions are stateless by default, and this allows them to scale out really easily, and also just to be able to reason with inputs and outputs without having to worry about any other state. Now, durable functions are stateful functions. Before you think, hold on, no, we're breaking the whole pattern of serverless here. It's still calling functions which are stateless, but it's adding some coordination between them in a stateful way. This allows us to write serverless patterns which are fairly common. And if we take a look down here, for instance, we've got function chaining, which is essentially a workflow. And these are fairly common, where you've got something that executes in a function. Once that's done, it needs to trigger something else and something else and something else. And we might tie those together with queues and adds it to a queue, and the next function picks it up from there, etc. Another one is fan out, fan in, where we spread out horizontally, scale out, and scale back in. Async HTTP pattern, and there are a few more, and I'm not going to go into the implementation details of these. The documentation is fairly good, and I've also created some videos on the different patterns and use cases for them. But what's interesting is that we use durable functions to write these in a way which it seems like we're writing it in process. So if all of these were in a single process, you would write it as first the one happens, and then the next line of code, the next happens, next happens, next happens. In a distributed serverless system, you write one function which is completely stateless and isolated from something else, and it needs to coordinate with the other one, maybe with queues, as we mentioned just now, and the other one picks it up from the queue. And by doing this, it actually means that we've got a lot of spread out logic and complexity to do a simple workflow. And it's the correct way to do it if you wanted to do it in a distributed system. But the problem is the complexity that it adds. Now, durable functions, if you look at the code over here, we're essentially saying F1 to F4. It's just F1 happens, and when it's done, F2 happens, and when it's done, F3 happens. And you may think that this is happening in a single function, but it's not. This is actually one function, which is the orchestrator function. Now, this is the important one. It's almost the glue that ties us all together, the thing that coordinates the various functions. And these are all separate functions that get called. And under the hood, we've got queues and we've got storage blob leases where for synchronization, and table storage stores the history so it can replay things. And we'll dive into that now. But when you write it, it's written in an easy way while still getting the benefits of stateless functions that we get from a regular function app. Let's take a look at some code. And you'll see what I've got over here is I'm using a normal HTTP trigger function, and it has this durable client context. Now, note that this is a little bit different to the documentation of Microsoft, and the reason for that is I'm using .NET 7, and I'm also using out of process functions, which is really neat because up until now, durable functions only worked in process. So what you do with the starter, and this doesn't have to be an HTTP trigger. This can be any trigger. So it could be a trigger from a service bus or something in blob storage that was put down. So any trigger essentially. And we use the starter to schedule the orchestrator function. The orchestrator function is where the magic happens. The orchestrator function calls the activity functions. Now, this is similar to what we saw in the documentation, where these functions are essentially external functions that are getting called, and it's written in in an almost in process way, as if we are just calling this and then this and then this in the single process. But these are all happening in separate processes, in separate stateless functions. Now, the pattern that's being followed here is the chaining or the workflow pattern in a sense. So what's happening here is we getting tools and parts, and then etc. We build the robot, a programmer test it. The details here are not that important, but I'd like to just take a look at what happens when we run this thing. So it's running, and I'm going to open up Postman here and make an HTTP request. Remember, we're using an HTTP trigger to get it started. And what you'll see is each step, it takes about 2 seconds each. And once we're done, we should see this message: completed robot, programmed, and it just checks all the results of all of this. And here we see that message as well. All right. So the function executed successfully. And what you'll see if we're scrolling through here is we are executing a whole bunch of functions. So this did not run in process, in a single process. We kicked off a separate function. If we go over here, fetching tools, that's a function on its own. And it will still run as a function on its own. And what's important to note here is that an orchestrator function is a special thing, and it needs to be treated in a special way. You can't do everything that you could do in a normal function or in a normal place. And we'll look at some of the examples of what you're limited to do there. But when you call an activity functions you can think of as the usual functions, the stateless ones, the ones that actually do the work. Orchestrator function coordinates things together in a workflow, fan out, fan in whatever way you want. Activity functions or entity functions, but the more common one is the activity functions. They are the actual functions that get executed here. The first thing you might notice is, hang on, if the orchestrator function runs, it kicks off this over here, which is a function on its own, which then waits for those results. So we've got 2 functions running here, right? You've got the orchestrator function, and then you've got the fetch tools function. And then when that completes, you've got this function running, and then the orchestrator function is still running until all of these are done. So this would seem like, hang on, this is a red flag. That's an anti-pattern in the serverless world, right? But we're not doing that, because the durable task framework that durable functions use is written in a way that when you call an activity function, it's a special function that once awaited, it actually exits the parent orchestrator function. And so what actually happens in code, and we'll see that now, let's put a breakpoint over here, is that tools gets called, the orchestrator function exits. As soon as tools have their results, the orchestrator function starts up again. And then parts gets called, and then it gets its results. But before it gets its results, the orchestrator function exits. Now, when it gets its results, the orchestrator function gets triggered again, but runs tools again. Now, this is really weird if you're not understanding how this was all tied together, because what actually happens then is there's a lot more glue to this whole statefulness. And the orchestrator function cannot exit and then start again in the middle. But what it can do is it can start again, but remember the results that it saved for fetch tools, for instance. So what actually happens is it sees, all right, but I've already done fetch tools for these parameters or inputs. In our case, this one doesn't have inputs, but for this case, it would. And if for the same inputs, for the same function, in the same orchestrator, it will see I've got my results, and it will actually just replay those results and not call the function again. So let's take a look. So I'm going to put a breakpoint over here. And then what I'm going to do is I'm going to just put a breakpoint inside of the fetch tools function. All right. And then we're going to put a few breakpoints here as well and show you what's happening. So let's kick it off again. Now what you see is we hit tools, right? Nothing weird here. I mean, that's what's expected. All right. If I step over, it actually goes into the fetch tools function. Now this is a separate function that gets executed if you have a look down here. And once that completes, it takes 2 seconds or so. We come down here to do parts. All right. And now that kicks off. I'm just going to run that. And suddenly you see, hang on, we're back to the top again. Now this isn't another execution. I haven't triggered it again. What's actually happening is that, once again, like I've said, is the orchestrator function exited as soon as it called the activity function. This is to prevent double billing. And so it allowed fetch parts to do its whole thing, which may take long, may not take long. Now, fetch parts, just to say here, is also limited to the 10-minute period, for instance, if we're using consumption plan. But if we're using the premium plan, for instance, then the timeouts are a little bit longer. But it's still limited to that. But what happens is then, as soon as that's done, it came back to the top now. Now, you might think it should go into fetch tools again. We still have a breakpoint over there, you see? But if I step over this now, I've got a tools response, but I didn't call it. And let's see how that's actually working. Let's open up Storage Explorer and take a look what's happening. So we've got blob containers for app leases or for leases. We've got queues that were created by the Durable Task Framework, and we've got table storage tables that were created. Now, if we take a look at the table storage, for instance, you'll see we've got various tasks that ran, and also the results that were run. And now this has to be a serializable result. That's a limitation as well from the orchestrator function. And the reason for that, both the inputs and the outputs, is so that it can actually store it over here. And if we're going back to replay it, you'll see this over here, these items are replayed back from table storage. But you might wonder, how does the orchestrator function know that it needs to now run again? And if we jump back to the queues, you'll see that one of these queues will have a message. Here we go. Now this is normal storage queue behavior, that as soon as a message is picked up, it doesn't show anymore, it becomes invisible. And should the process fall over, for instance, it'll become visible again. But should it complete, then it'll be removed. So there we go. There's a message here now. So that was picked up by the orchestrator function, and that was then run and replaying these results. So what about exceptions? What happens if something goes wrong? Now, and also, what about durability? Like, what if this process fell over? How does that all work? And it's actually quite resilient in the sense that an orchestrator function will make sure that all activity functions are run executed at least once. Now, I say at least once because there is a very slight chance that an activity function can run twice. And the scenario that would happen was an activity function was kicked off by the orchestrator function. It actually completed, and something went wrong the very moment it tried to write the results to the table storage, the orchestrator function. In which case, when the orchestrator function runs again, it doesn't see the results yet, and it will run it again. So, although very unlikely, it is best to write the activity function as idempotent as possible, meaning that you can run them twice and you shouldn't have side effects. With that in mind, something that is quite useful for developing, because you get strange scenarios where you've stopped something and you started it again, and because of the stateful nature of this and the resilience that it allows it to pick up an item from the queue, then run it again, and some of the results have already been run, that you may end up in a scenario where you change something and you checking why is it not running, or why is it skipping over it, or something like that. And or why is it suddenly just hitting this breakpoint? I didn't call anything. And so something that's quite useful I got from Chris Gillum, on his site. He's one of the guys also helping to build the .NET 7 durable task framework. Is there is a function just to clear the states. And so what we do over here is we just do something like this. I've made it into a function as well, which allows us to just go in over here, clear everything, and as soon as that's cleared, you can go back to storage and refresh, and you'll see actually these are all gone. So that just makes development easier, especially if you're making changes and you've done half runs and those kind of things. And you may have noticed that if we've gone back to our original HTTP trigger, that once we trigger this, we get some results here. Now that's due to the starter. When we create the new orchestration, we actually returned with this create check status response. But it gave us a nice way to get hold of some URLs that we can call. Now, if we were to call the status one, for instance, and executed that, you'll see that it's pending. So, and if we let this run a little bit, etc., we can run it again, and there you see the status is running. So this actually gives us URLs where we can, this whole orchestrator that is busy running, we can actually poll it and see, is this thing running, is it not? And that's one of the patterns actually you'll see in the documentation in the beginning, is where you can kick off something, get a URL for that, and a client or some a front end can then just check every once in a while what's the status of this thing. And once it's completed, it knows that the whole orchestration process is done. And that's quite useful because, once again, functions are stateless by nature. So if you have a whole bunch of them coordinating things together, it's really difficult to know the status overall, because you're going to have either another function running that kind of monitors it, or everyone must save it in a certain place, and then the function checks all the results, something like that. We get some other ones over here. So for instance, if you want to terminate, you want to stop the process, we can call that as well. And then this one is the purge history. So if you wanted to purge the history, similar to what I did with that function, you can do that. Now, the reason I wrote the function instead of just doing this seems a lot easier, right? Is that I sometimes run things multiple times. So I might just stop this here, make a change, run it again, and then I trigger that function again, the HTTP trigger, which gives me a new URL. You'll see the ID has changed. Now, I don't know what the old ID was, and I didn't save it. So I would have to go back on all the different IDs that I had run and call purge on all of them. So that's why it's just easier to call that other function that clears things out. Let's look at some error handling, for instance. So if I were to go into fetch parts, for instance, and over here, while we're fetching parts, we'll say throw a new exception, something explodes, right? So that fails. The wonderful thing about this is, even though this is in a whole different function, in a whole different process, I can try catch around it, which is mind-blowing. I really find this amazing. So what we can do over here, is just take that. We'll need the parts just to be up here, for instance, and over there. So we can call the parts, we can do some error handling. Maybe what we want to do is log it out, but we might not want to throw everything out, for instance. We might want to say, okay, no, carry on. If this happens, that's all right. Carry on as we were. And so if we were to run this again, now I'm going to call the HTTP trigger. And what you'll see is it pops in here. And similar to earlier, it jumps into that first function. Give it some time. Once we get to the parts over here, let's just put a breakpoint over here. Goes back to tools, replays that message. It didn't take as long this time because it had the results already. Throws an exception. Let's pause here. Now, this is not some magical exception that somehow went to the other process and fetched it. What actually happens is the exception was thrown, once again, serialized, put away. So in theory, we should be able to go back here now. Let's just refresh. There our tables are back again. Refresh. And we must actually let this one run through. Then we'll see it. But it's a task failed exception. And that's the specific exception that gets serialized. So the failure details are serialized. There's our exception. The task name is the name of the task that failed, task ID, and those details are on that type. So it always throws a task failed exception. So if we run this again, and we get to the next stage because we didn't throw from there, we actually swallowed the exception, decided we don't need all the parts. So once we go back, now what will happen is if we look in here, we should have an exception message over here. There's our exception. Boom, there's a full stack trace. And what actually happens, and it's pretty cool because if I put a breakpoint here, is I come in here again. Remember, this thing runs again. And it doesn't replay. It doesn't recall this function. It replays the message, but it actually looks up and says, hang on, I threw an exception last time. So it builds up an exception, and the durable task framework serializes the exception message and throws that again. There we go. And you'll see we got the exact same error message again, exception with the stack trace and everything, but this wasn't called at all this time, which is pretty neat. And then from there, it can run on. So earlier I alluded to the fact that there are limitations in the orchestrator function. And so some of those limitations that we have are, for instance, everything inside this has to be deterministic. So what that means, for instance, is if this is my input over here, build input, but I suddenly now have a date over here in this input type, and I say datetime.now. Remember, this thing will replay it, or play it the first time, datetime.now, then it will hit here, it will go to sleep, and then once it's woken up again, what will happen is it replays all of this, but this time datetime.now is different. So what happens is the input is different, which means it thinks that this is a new call. So we're essentially going to get stuck building this robot over and over and over and over again. So this is non-deterministic because if I run it now and if I run it now again, it's going to give me a different result. Same with a new GUID, for instance, that's going to be the same problem. So things like that, we have to make sure that we don't have those in the orchestrator function. If you need to use datetime now, you can use it in the build function. There's nothing wrong doing it over here. Remember, the activity function will only be called once for that input, and we can capture the date there. Or if you wanted one date that you want to maybe create on top here, which might be a valid scenario, and pass the date everywhere, rather than we can create things like activity functions which fetches the date or something, or a non-deterministic thing, a random number or something like that. And that way, it saves the date to table storage, and then every time it replays, it gets the same date. So the first time the date hits, it gets the date, and then from there on, the results are the same. A few other items that are non-deterministic and fairly commonly used, things like random numbers, for instance, static variables, those shouldn't be used. Environment variables is another one. Don't stay away from those. Once again, not stay away from those completely, but inside the orchestrator function. If you want to run asynchronous calls, let's say you want to reach out to another web server or service or something to get some results, never do that in the orchestrator function as well. We're probably going to run into a deadlock or something like that because orchestrator functions run on a single thread and they can't interact with other threads. And so things just go crazy if you start to do that. Things just go weird. So just note, don't write async await that is not to an activity function or an entity function or something specifically built. An orchestrator function should purely be to organize and coordinate calls to activity functions and entity functions. There are a few helper methods on the context that you could use, and those make it easier if you wanted to do an HTTP call. Ideally, call an activity function, but if you just want to do a raw HTTP call, for instance, there are some helpers that you can use on the context. But once again, as soon as you obviously add any other functionality to that, best to just create an activity function and then call it from there. Also, don't use any task.delay, things like that. Once again, anything asynchronous specific, task.run, all of those things, just stay away. The orchestrator function, just use the activity functions and coordinate the code. That's it. And so there are some helpers that you can use there. There are ways we can call timers to say, pause for so long, those kind of things. Wait for external events. So wait till some event happens, which can be triggered in another function or externally or something like that. And as soon as that trigger happens, then it carries on. So there are quite a lot of built-in things that you can use with the durable task framework that help you. But in short, when in doubt, keep it simple in here. And the only async thing you should write are activity functions and entity functions. And entity functions is something I haven't mentioned in here, but they're essentially similar to activity functions. They're the kind of functions that do the work at the end of the day, but they are in a way something you would use when you're trying to write some form of state machine. So for instance, if you want to do pull requests, you need to have it build, run the tests, you need 2 approvers, you need comments resolved, those kind of things. And if each of those happen at any time, I mean, you could have the build complete or you could have it approved. Who knows which one happens first? Instead of having to check which one is done or having something else, that's a good way to write a state machine where it's you're not going to run into race conditions. This essentially allows you to call it and you can handle one event at a time, and you're guaranteed to have that thread safety in a way. Although thread safety is the wrong word because it's not in process. But the idea is you're going to have them synchronized. And then finally, if you want to check out the Durable Task Framework, there's a lot more info on there as well. This is the .NET 6 one, the Azure Durable Task, and it's open source. It's on GitHub. All the code's there. You can go through the README. The Microsoft documentation is really good around durable tasks as well, durable framework functions. Sorry. The only downside is the Microsoft documentation isn't up to date when it comes to .NET 7. It is still in preview, and it does use a different durable task framework. So that's this one. That's the one that I'm using currently. Note, it's not ready for production, but it will be soon. It's almost November, and .NET 7 will be released, and I'm sure that this is going to be ready, or at least close to ready, around the time of the official .NET 7 release. So looking forward to that. Looking forward to writing isolated functions where I can do my own dependency injection and all of that, and not in process as before with durable tasks. This is just going to be amazing when you use complex scenarios, or it's actually fairly common scenarios, but they are complexly written because of all the coordination. And this is just going to make life so much easier. Write one orchestrated function, coordinate it all, try catch, all of those things, and we're good to go.